Hello, calculus fans. I'd like to talk about the Heaviside cover-up method. Okay, so this is a technique for solving for the constants when we do a partial fractions decomposition. And it can be very fast and very efficient, so I think this is worth learning because up to this point we've been solving systems of equations, which can be really slow. The downside of the Heaviside cover-up method is it doesn't really always work, but it does for very simple decompositions. Okay, so let's suppose we had a fraction that looked like this. So I've already done the factorization in the denominator, and we want to do a decomposition. So the form of the decomposition looks like this. So a over x minus 2 plus b over 2x plus 3 plus c over x plus 1. All right, let's say we want to find a. So what we're going to do is we take the left-hand side and cover up x minus 2. Why am I covering up x minus 2? Because that's the linear term that corresponds to a. So I'm going to cover this up. And we're just going to cover that up like that. All right, nicely covered up. Of course, when I go to my next slide, that's going to be all gone. Okay, we're going to find a. So we cover up the x minus 2. So it looks like that. Well, that's not a very good cover. All right, let's cover it up. Gone, 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 gone. So the leftover piece looks like this. So that's with that piece, the x minus 2 missing. And I want to plug in x equals 2. All right, why am I plugging in x equals 2? Because that's the thing that makes the denominator underneath a equal to 0. Right, what was underneath a? It was x minus 2. And what would make that equal to 0? It would be 2. So that's what you're going to plug in. So that's going to give us the a. If you plug in 2 into the leftover portion here, you find out what the value of a is. Okay, now this is a pretty horrible looking value, but I went ahead and worked it out. It actually comes out to 5. Okay, let's try to solve for b. So we take the left-hand side of the original decomposition and cover up 2x plus 3. So that's what we're doing. We're covering up the 2x plus 3 here. Let's cover it up. Gone. Okay, that's gone. And now we take the leftover portion, which looks like this, whatever's left over after having covered that up. And now, what are we going to plug in? We're going to plug in x equals negative 3 halves. Okay, why negative 3 halves? Because that's the number that makes the expression underneath b equal to 0. Remember, what was underneath b? It was 2x plus 3. And what if I set that equal to 0? Could you solve for x? Sure you could. And you'd end up with x equals negative 3 halves. And so that x equals negative 3 halves is what we're going to plug into this expression. That's going to be what b is. And I went ahead and worked all that out too, and I got 11. All right, so let's see if you can calculate what c is. Go ahead and take a moment to try to calculate what c is, just to make sure you can do it for yourself. All right, pause the video now and do the calculation for c and find out what you get. If you did it right, you should end up with c is equal to negative 7. Now, I think it's worth warning you that the cover-up method, Heaviside's cover-up method, it doesn't work for all the constants. It will not work anytime you have a term that corresponds to an irreducible quadratic. And it will also can only be used for the highest order term for any particular linear factor. So to demonstrate what I mean, let's take this decomposition. Oh, this looks like a mess. So there are a couple of repeated linear terms down here, and then a repeated quadratic term. So when we write out the decomposition for the quadratic term, the cover-up method can't be used for any of those. In fact, it can only be used for the highest order term of the repeated linear factor. And if you think about it, if you try to do it with, say, this term here, it doesn't work because when you cover up only one of the 3x minus 1s, then you're going to have to plug in something that'll make the denominator 0. So that won't work. And then I should also warn you that if the degree of the numerator is larger than or even equal to the degree of the denominator, then the first thing you have to do is perform long division. We'll talk about that more. Okay, that's all for now.